Congratulations, you've made it to section 7E, the very last section of Math 108. Again, I'm going to preface this. I know you've heard it before. Read the section before you watch the video lecture just so that you get more out of it, and it'll kind of fill in all of the holes as well that I don't cover. All right, section 7E is about arrangements and repetition, also permutations and combinations, and then we'll throw in a little bit of some probability in there as well. The first thing we're going to talk about is arrangements with repetition. Let's suppose there are 7 places for digits 0 through 9 on a license plate. How many possibilities are there? I am a visual and tactile learner, so I like to take my pen and draw out 7 spaces for my digits. And so what I've done here is I've made blanks. 1, 2, 3, 4, 5, 6, 7 blanks. Now, digits 0 through 9, a lot of you are going to say that's 9 digits, but don't forget that 0 needs to be counted as well. So if I count 0 as 1, count the 1 as a 2, so 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that shows you 10 different digits that you can use. So for each of these spaces I have 10 possibilities because I can repeat these numbers. I could have a 1, 1, 1, 1, and so forth. And so for each of these I have 10. 10 times 10 times 10 times 10 times 10 times 10 times 10 is 10 to the 7th. Or, give me 7 zeros, 1, 2, 3, 4, 5, 6, 7 is 10 million possibilities. Now we've already done a little bit of this when we found the different sizes for the truth tables, and also again when we talked about finding all of the outcomes for when we started with probabilities. So this is pretty familiar, I'm hoping. Let's look at our first example. How many 7-symbol license plates are possible if numbers and letters can both be used? So I have 26 letters in the alphabet and 10 digits 0 through 9. That gives me 36 possibilities for each of my 7 spaces. So I'm going to draw out my 7 spaces. If you're using your pen and paper, just draw out 7 lines to show that this is a space representing each of those on my license. And then I have 36 possibilities for every single one of these because I can repeat the repetition. Then I get 36 times 36 times 36 all the way up to 7 times, which is 36 to the 7th. Let's move to the next example. How many 6-character passwords can be made combining upper and lowercase letters and numbers, those digits 0 through 9, and the symbols of and, at, and the $sign? Just 3 symbols. So we have 26 uppercase, 26 lowercase, 10 digits 0 through 9, and 3 symbols. Add those together and I have 65 possibilities for a 6-character password. So each of these characters I have 65 possible, 65 possible, 65, 65, 65, and 65, which gives me 65 raised to the 6th power. Now if I wanted to find the actual number for that, and I don't have to, but if I wanted to, I would, I have a couple of things in here. Let's take those out. Equals 65 caret is raising to the 6th gives me a very large number of, let's see, comma there, comma there, comma 1, 2, 3, 1, 2, 3, 1, 2, 3, 75,418,890,625 possibilities just by adding in a couple of those other things, upper and lower case digits and symbols. It's kind of nice to know that there's different ways to make sure that you're picking really good passwords. Let's move to 2. Roman numeral 2 is permutation. Permutations are where order matters. So let's move to a 4-person relay team. How many different arrangements can this 4-person relay team have? Now, one person, because it's a relay team, can't be in the first position and in the last position, which would be our arrangement with repetition. So here, my 4-person relay, I have 1, 2, 3, 4 spots. The first spot, I can pick 4 people to go in this first spot, but once I pick that person, I now only have 3 people left to fill in the second spot. then I only have 2 people left, and the last one I only have 1 person left. 4 times 3 times 2 times 1. 2 times 3 is 6, times 4 is 24, times 1 is still 24. There are 24 possible arrangements for my 4-person relay. Another way of looking at this is called 4 factorial. 4 factorial is 4 times 3 times 2 times 1. A factorial is represented by just an exclamation mark. Factorial means that I take the number and every number subsequently less than all the way down to 1 and multiply them. So 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, and so on. And I didn't go any higher because then that would take a really long time. 1 factorial is just 1. That makes sense. 0 factorial is also 1 by definition. You just have to memorize it. Let's move to our next example. Class schedules. A middle school principal is trying to find how many different schedules are possible. He has 6 classes: math, English, history, Spanish, science, and gym. And there are 6 time periods available for each schedule. So I'm going to make my 6 lines dash, 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 and dash. And then I look through it and see what's possible for what. I have 6 classes to choose for the first period. But once I choose that, I only have 5 for the next one, 4 for the next one, 3 for the next one, 2 for the next, and then of course 1 for the last one, which I could rewrite as 6 factorial or 720. If you wanted to do that in your calculator, those of you who have a graphing calculator, it's usually the math button. And the math button is just second math on most of those. Or in Microsoft Excel, you can do fact. See how it says factorial of a number? Fact, parenthesis. I want to find the factorial of 6, close parenthesis, enter 720, which is what we got. So if I have a 10-person swimmer, or 10 swimmers in a 4-person relay, I have 4 spots. 1, 2, 3, 4. So my first spot, I have 10 options for the first position, 9 for the next, 8 for the next, and 7 for the next. Multiplying those gives me 5,040 different orders for the relay. So this one didn't go all the way through 10 swimmers in a 10-person relay. This is 10 swimmers selected 4 at a time. This is written as 10 permutation 4. Now the reason for this is I have 10 swimmers and I'm choosing 4 at a time, and there's different swimmers that I can pick for my 4-person relay. And remember, order matters because I can't have somebody swim the first and then jump in and swim at the end. It's a relay, so the order is mattering who is in what position. So this is what it looks like. 10 permutation, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And the difference between these is 6, 5, 4, 3, 2, 1. And these dividing can be canceled out by using the strike through function. You can show that with your work, because 6 divided by 6, 5 divided by 5, 4 divided by 4, 3 divided by 3, 2 divided by 2, and 1 divided by 1 all cancel out, or you can think of it as dividing and equaling 1. And that's rewritten as 10 factorial over 10 minus 4 factorial, which is our formula. This is n permutation r. Now if you're wanting to write that in your own notes, you can do the subscript of n, click it to get out of the subscript, permutation, go back to the subscript, r equals, and you can go up and insert an equation just like we did in our previous sections. Insert new equation, and here we would write a fraction. I like it like the line fraction, and we have n, and just do shift 1 over parenthesis n minus r, close parenthesis, Shift 1, there we go. So that's how you would type it into your own notes. Or the same for your multiplying and writing it out longhand, and then just highlighting what you want to show that you're going to cancel it out and using the strike through application. Let's move to our next example. The city has 12 candidates running for 3 leadership positions: mayor, deputy mayor, and treasurer. The top vote of these 12 candidates will be mayor, the next top vote will be deputy mayor, and the next would be treasurer. Now this again, order matters because the person who gets the top vote can't get the top vote and the next top vote. That doesn't make sense. So order is mattering because the mayor gets the first, the deputy the second, and the treasurer the third. How many possible outcomes are there for these positions? Remember, I have 12 candidates. So I have 12 total people, and I'm going to choose 3 of them for the different possibilities for these positions. Using my formula, 12 factorial divided by 12 minus 3 factorial. 12 factorial is 12, 11, 10, 9, 8, all the way down to 1. 12 minus 3 is 9, so I get 9 factorial, which is 9, 8, 7, 6, 5, 4, 3, 2, 1. Now I could have written that all out and gone from 9 down to 1. But I'm going to stop here because I know 9 factorial and 9 factorial are the same thing. 9, 8, 7, 6, 5, 4, 3, 2, 1. Just like what happened up here, I know all of these factors. 9 down will cancel out with this one, 9 and down. And I'm left with 10, or 12, 11, and 10. 12 times 11 is 132. Times it by 10 is 100, or 1,320 possibilities of these 12 candidates and these 3 leadership positions. Let's talk about batting order. How many ways can a manager of a baseball team form a 9-player batting order with a roster of 15 team members? So the number of people is 15, permutation 9 positions. So I have 15 factorial over 15 minus 9 factorial. 15 minus 9 is 6. So up here I'm going to do 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, and I can keep going, but I know that this is also 6 factorial. So to speed us up, and you don't have to, you can keep going. You can do 6, 5, 4, 3, 2, 1 so that you can show that it's canceling out just like we did up here in the swimmers. But just to speed us up, I'm going to stop, cancel out the 6, and I'm left with 15, 14, 13, 12, 11, 10, 9, 8, 7, and I can highlight those, and copy just those numbers, go into Microsoft Excel, equals, Control V, enter, and there's my answer. I can copy and paste that back in, but I already have it here. Oh, I am not going to put that exclamation mark there because that would look like a factorial. That is 1,816,214,400 different batting orders for this 9-person batting order with the 15 team members. Let's move to combinations, Roman numeral 3. This is when order doesn't matter. So if I were to have like a 3-person committee with 4 people, I can combine 3 people, and so I have Abby, Brenda, Carla, and Dan. And a committee of Abby, Brenda, and Carla is the exact same committee as Brenda, Abby, Carla, Carla, Abby, Brenda, Carla, Brenda, Abby, and Brenda, Carla, Abby. Did I say that one? Carla, Brenda, Abby. They are all the exact same committee. It doesn't matter the order. So our formula needs to be slightly different. I need to divide out all of these replications because these are all the same combination. So the formula changes just slightly. It's n factorial over n minus r factorial times r factorial on the bottom, and that gets rid of all of these same combinations. Now, I like to use this as stating it is n combination r, but I like to think of it as n choose r. I have n possibilities and I'm going to choose only r of them. That helps me also on permutation, even though it doesn't say choose, but I kind of think of that in my head. I have n number of possibilities and I'm choosing r number of possibilities, but in a permutation the formula is slightly different. So here I'm going to do my 4 persons, Abby, Brenda, Carla, and Dan, for my 3-person committee. So I have 4 people. Choosing 3 of them gives me 4 factorial over 4 minus 3 factorial times 3 factorial to get rid of all of these duplicates. So 4 factorial is 4, 3, 2, 1. 4 minus 3 is 1 factorial, or 1. 3 factorial is 3 times 2 times 1. 3 times 2 times 1 cancels out with 3 times 2 times 1. Oh, went too far. Cancel those out, and I'm left with 4 divided by 1, which is 4. And let's highlight that as my answer. There we go. Let's try the same combination with the 4 previous people, but now we're going to add an Emily. So we have A, B, C, D, and E. So now I have 5 people, and I want to choose 3 or a combination of 3, which gives me 5 factorial over 5 minus 3 factorial times 3 factorial, which gives me 5, 4, 3, 2, 1 by the definition of factorial. 5 minus 3 is 2 factorial, which is 2 times 1, and 3 factorial is 3 times 2 times 1. Again, these ones cancel out with these. Then I'm left with 5 times 4 over 2 times 1, which I could say is 20 divided by 2, which is 10, or I can cancel 4 by 2, which gives me 5 times 2, which is 10, either direction. And let's highlight that as the answer and move to the next example. Ice cream combinations. We're going to select 3 flavors of ice cream from a store that carries 12 flavors. How many combinations are there? Now remember, this is a combination. If I were to get vanilla, chocolate, and strawberry, it's the same as strawberry, chocolate, vanilla, and vanilla, strawberry, chocolate, and all of those together. They're the same thing. So this is a combination. 12 flavors, choosing 3 of them gives me 12 factorial over 12 minus 3 factorial times 3 factorial. So 12 is 12, 11, 10, 9, all the way down. 12 minus 3 is 9 factorial, 9 down to 1, divided by 3 factorial, 3, 2, 1, and I can show that these 9 factorials cancel. I can go through also and simplify some more. 3 times 2 is 6, 12 divided by 6 is 6, 6 times 11 is, 12 divided by 6 is 2, 2 times 11 is 22, 22 times 10 is 220, different combinations from this store. Let's move to the next example. In poker, you have 5 cards for a hand in poker, and there are 52 cards in a deck. How many 5-card combinations are possible? And then what's the probability of a royal flush? So what we're going to do first is find the combination of 52 choose 5, so 52 factorial over 52 minus 5 factorial divided by 5 factorial. Now this one's not as easy as the ones that we've done previously. So you can use your calculator or go ahead and use Excel. You can come in and do combination 52 combination 5. So equals combin, and it's going to prompt you of the number or n. We have 52 cards, and choose 5 cards for the hand, close parentheses, and we get, let's see, comma here, 2,598,960 different combinations. There we go. All of those different combinations of 5 cards out of the 52 cards in a deck. Now, a royal flush are the royal or the upper cards, I guess you would say, in the deck, and there are 4 suits possible for all of the royal flushes, so there's 4 possible royal flushes. So the probability, now we're kind of mixing the previous sections with this one now. 4 royal suits over 2,598,960. And we could find that decimal if we'd like. We could say equals 4 divided by, and I'm just going to reference that cell so I don't have to type it all out. Let's change that, format the cell so we can see what it looks like. There we go. Let's go to number, and we're going to give it a bunch of decimal places. Hopefully that'll, oh, we're still not there. Go back and format it. We need some more decimals in there. There we go. There's our decimal. So the probability of getting a royal flush is pretty rare. Let's move to the next one, winning the lottery. So with this lottery, there's 6 balls that pop up with numbers on them, and there's 52 numbers. So what's the probability that your 6 numbers will be chosen? So the first thing we need to do is find all of the outcomes possible, right? Remember when we want to find probability? So I need 52 combinations of 6. Now remember, it's a combination here because it doesn't matter the order that these balls pop out for the lottery. Those of you who haven't played, now you know the order doesn't matter, the number's on there, and you're good to go. So I have 52 numbers divided by 52 minus 6 times 6 factorial, and toss this into Excel because you aren't going to try and do that one by hand. And we do 52, choose 6, so equals combine or combination of 52 numbers with 6 balls chosen. The total number of combinations of 6 number combinations is 20,358,520, which we have here. Now that was just all of the possibilities. What's the probability that your 6 numbers are chosen? Well, out of all of those combinations, yours is 1. So 1 in 20 million that you will win. Let's find the probability. Equals 1 divided by this. And again, I think we're just going to try Format Painter. There we go. And how many decimals is that? 1, 2, 3, 4, 5, 6, 7. 7 zeros before. So the probability of you winning the lottery is, well, I'll let you decide. Pretty insignificant. All right, that is the very last section for Math 108. Good luck on your final and the rest of your homework.